When you strike a bell, it rings. When you pluck a guitar string, it vibrates. Even the air in this room carries tiny ripples of sound as I speak. We are used to the idea that objects can sing. They vibrate, they hum, they resonate. Now imagine something that swallows light itself, something so dense that not even radiation can escape its grasp. A region of space-time from which there is no return. Would you expect that to sing? Simple enough, right? But here's the thing. A black hole is supposed to be silent, utterly silent. It has no surface to strike, no atmosphere to vibrate, no material shell to oscillate like a drum. It is defined by absence, by darkness, by the inability of anything, even light, to climb back out once it crosses the boundary we call the event horizon. So how could such an object produce anything resembling a sound? Stop and think about what this means. If a black hole sings, then it is not completely black, not completely silent, not completely sealed off from the rest of the universe. That simple idea unsettled me for decades, because when I began my work on black holes, the consensus was clear. They were perfect prisons, cosmic traps with one-way doors. Matter falls in, information falls in, nothing comes out. End of story. But physics rarely ends so neatly. Think about the vacuum of space. We call it empty. We picture a vast dark nothingness between stars. Yet quantum theory tells us that even in the emptiest regions, something is happening. Tiny fluctuations, brief flickers of energy, particles and antiparticles appearing and disappearing in pairs. They borrow energy from the universe, exist for an instant, then annihilate each other and return that energy, like bubbles forming and popping on the surface of boiling water, invisible, fleeting, but real. Now place such restless emptiness at the edge of a black hole. Here's where the story becomes strange. At the event horizon, gravity is extreme. Space itself is stretched to its limits. Time behaves differently. The boundary is not a solid wall. It is a point of no return written into the geometry of space-time. And geometry can influence quantum fields. Same pattern, same physics. If quantum fluctuations occur everywhere, they must also occur at the horizon. But at the edge of a black hole, something unusual can happen to those fleeting pairs of particles. Normally they annihilate, they cancel out, nothing remains. But near the horizon, gravity can separate them. One falls in, the other escapes. And to a distant observer it appears as if the black hole has emitted a particle. Let me say that again. It appears as if the black hole has emitted something. Radiation, energy, a whisper. Now things get strange. If particles are escaping, then the black hole is losing energy. And if it loses energy, it must lose mass. And if it loses mass, it cannot be eternal. A black hole can slowly evaporate. That was the implication of my calculations. A result that surprised even me, because it means a black hole is not just a gravitational trap. It is a thermodynamic object. It has a temperature. It emits radiation. It behaves, in a sense, like a hot body. And temperature means vibration. It means fluctuation. It means something akin to a faint cosmic hum, not sound in the way your ears perceive it. There is no air to carry pressure waves in deep space, but a deeper kind of song, a quantum melody written into the structure of space-time itself. Think about that for a moment. The darkest objects in the universe are not silent after all. They glow, very faintly, almost imperceptibly, but undeniably. This radiation would later bear my name, not because I owned it, but because I had the privilege of uncovering it. And yet the discovery raised a more disturbing question. If black holes can evaporate, if they can slowly disappear, then what happens to everything that fell inside? What happens to the information? That mystery would lead us into one of the deepest paradoxes in modern physics, and it begins with a whisper at the edge of darkness. Let us begin gently. Imagine you are standing at the edge of a waterfall. The river flows smoothly toward the brink. Then suddenly it plunges downward. Once the water passes that edge, it cannot climb back up. The boundary between calm river and falling torrent is clear. That boundary is like the event horizon. Simple enough, right? But here's the thing. If you drop a leaf into the river before the edge, you can still retrieve it. Once it crosses the brink, it is gone forever. That is how we traditionally pictured a black hole, a cosmic waterfall where space-time itself is flowing inward faster than light can swim outward. Now think about the air above that waterfall. Even though the water falls in one direction, the air above it is restless, swirling, fluctuating, invisible currents moving unpredictably. Quantum fields behave in a similar way. Even in what we call empty space, fields are never truly still. They jitter, they fluctuate, they briefly produce particle pairs that appear and vanish. This is not speculation. It is a direct consequence of quantum theory. Now place this restless quantum sea at the edge of the gravitational waterfall. Here's the thing. Gravity at the horizon is so intense that it distorts these fluctuations. Normally, when a particle and its partner appear, they reunite and cancel out almost instantly. But near the horizon, the flow of space-time can pull them apart before they annihilate. One is dragged inward, the other escapes outward. To a distant observer, it looks as though the black hole has emitted a particle, as if it has radiated energy. That radiation carries energy away, and energy has a cost. Stop and think about what this means. In Einstein's famous relation, energy and mass are equivalent. Lose energy, lose mass. If a black hole emits radiation, it must slowly shrink. That is the remarkable conclusion. Now things get strange. If a black hole has temperature, then it must also have entropy. Entropy is a measure of disorder, or, more precisely, a measure of how many microscopic configurations correspond to a macroscopic object. Think about a deck of cards. From a distance, it is just a deck. But shuffle it, and there are countless arrangements hidden within that simple description. Entropy counts those arrangements. For an ordinary object, entropy is related to its volume. More space means more ways to arrange its internal components. But for a black hole, the entropy is not proportional to its volume. It is proportional to its surface area, specifically the area of the event horizon. Same pattern, same physics. That result was deeply unsettling. It suggests that the information about everything that has fallen into the black hole is somehow encoded on its surface, not buried within some hidden interior, like words written on a sphere of darkness. Think about that for a moment. A three-dimensional object whose fundamental description depends on a two-dimensional boundary. This hints at something profound. It hints that space-time itself might behave like a hologram, where the true information content of a region is stored on its surface. But let us not rush ahead. First, consider the temperature itself. The smaller the black hole, the hotter it becomes. As it radiates and loses mass, its temperature rises. It radiates more intensely. It shrinks faster. A runaway process. Eventually, in theory, it would explode in a final burst of radiation. A dramatic ending. Yet for stellar black holes, this process is unimaginably slow. Far longer than the current age of the universe. The song is faint, the evaporation almost imperceptible, but it is there, a whisper of quantum mechanics echoing against gravity. And this whisper creates a tension between two great pillars of physics. On one side, general relativity, smooth space-time, deterministic evolution, information preserved in the geometry of the cosmos. On the other side, quantum theory, probabilities, fluctuations, uncertainty woven into reality itself. Black hole radiation forces these two frameworks into conversation, and they do not speak the same language easily, because if a black hole can evaporate completely, carrying away only featureless radiation, then information about what fell inside appears to vanish. That would violate a core principle of quantum mechanics. So we are faced with a paradox. Does information truly disappear, or is it somehow hidden within the radiation in a subtle, encoded form? Here's the thing. To answer that question, we must look more closely at what we mean by information itself. And once we do, the mystery deepens beyond anything we first imagined. What is information? At first glance, the question seems almost philosophical, but in physics, it has a precise meaning. Information is the complete description of a system. Every detail, every configuration, every quantum state. If I burn a book, the pages turn to ash and smoke. The words are gone from sight. But in principle, if you could track every molecule of smoke and every particle of ash, the information is still there, scrambled, dispersed, but not destroyed. That is a central principle of quantum theory. Information is never lost. Now place a book near a black hole. Let it fall across the event horizon. From the outside, the book disappears. Its atoms, its structure, its words, all swallowed. The black hole grows slightly more massive, slightly larger, but if the black hole eventually evaporates, radiating away its mass as thermal radiation, what happens to the information contained in that book? Here's the thing. Thermal radiation is random. It carries no obvious imprint of what formed it. It is like the uniform glow from a hot stove, featureless, anonymous. If a black hole evaporates entirely into such radiation, then the detailed information about the book seems gone forever. Stop and think about what this means. If information can truly vanish, then quantum mechanics is incomplete. Its core symmetry would be broken. The evolution of the universe would not be reversible in principle. That possibility disturbed me deeply. For years I argued that information was indeed lost, that black holes destroyed it. My calculations seemed to imply this conclusion, but many of my colleagues disagreed. They believed that information must somehow escape, not in an obvious way, not in a readable form, but encoded subtly within the radiation, like a message hidden in static. Now things get strange. If information is preserved, then the radiation emitted by a black hole cannot be perfectly random. It must contain correlations. Tiny connections between particles emitted at different times. Each quantum of radiation would be entangled with others, a delicate web of relationships stretching across the entire evaporation process. Entanglement is one of the strangest features of quantum theory. Two particles can be linked so that measuring one instantly determines the state of the other, even across vast distances. Same pattern, same physics. At the horizon, the escaping particle and its partner that falls inward are entangled. Their properties are linked. But if the black hole evaporates completely, what happens to the partner that fell in? Does the entanglement break? Or is the information somehow transferred outward gradually over time? Think about that for a moment. If the outgoing radiation carries hidden correlations, then the black hole is not a simple destroyer. It is more like a complex processor, scrambling information, delaying it, but ultimately releasing it back into the universe. That idea leads to a remarkable image. Imagine the event horizon as a kind of membrane, a dynamic surface storing information in microscopic degrees of freedom, each bit encoded on an area the size of the Planck scale, unimaginably small. The black hole would then behave like a hologram. Everything that falls in is recorded on its surface, and as it evaporates, that information leaks out in subtle correlations within the radiation. This perspective reshapes our understanding of space itself. If the maximum information contained within a region scales with its surface area, not its volume, then perhaps the universe at its deepest level is not truly three-dimensional. Perhaps our familiar world emerges from information encoded on distant boundaries. That is the holographic principle. Simple enough, right? But it suggests that gravity, space-time, even reality as we experience it might be emergent phenomena, collective behaviors arising from more fundamental quantum bits. Black holes become laboratories for this idea, extreme arenas where gravity and quantum mechanics are forced into union. And the song of a black hole, its faint radiation, becomes a clue that the universe protects information at all costs. Yet the full reconciliation remains incomplete, because when we calculate the entanglement structure near the horizon, contradictions appear, firewalls, paradoxes, deep tensions between consistency and smooth space-time. We are left at the edge of understanding, a boundary as sharp and mysterious as the event horizon itself, and beyond it lies a possibility even more profound than the paradox we began with. We have followed a whisper to the edge of darkness, a faint radiation from an object once thought perfectly silent, a slow evaporation from something once believed eternal, a paradox that challenges the foundations of physics. Now let us step back. A black hole begins as the collapsed core of a massive star. Gravity overwhelms all other forces. Matter compresses beyond any familiar state. An event horizon forms. From the outside, it seems simple. Mass, spin, charge, nothing more. That simplicity is deceptive. Here's the thing. If entropy is proportional to the area of the horizon, then every square patch of that surface carries information. Tiny bits, quantum degrees of freedom. The black hole is not empty. It is saturated with hidden structure. Think about that for a moment. The most featureless objects in the universe possess the largest entropy per unit volume. They are, in a precise sense, the most information-dense entities we know. That is the beautiful part. The song of a black hole is not music in air. It is the slow release of encoded history. Every particle that fell in, every quantum fluctuation at the horizon, all woven into a subtle pattern within the outgoing radiation. We cannot yet decode that pattern, but theory insists it must exist. Simple enough, right? But if information is preserved, then the universe is fundamentally unitary. Its evolution is coherent. Nothing is ever truly erased. Events may become inaccessible. They may be scrambled beyond practical recovery. Yet in principle, the ledger of reality balances perfectly. Stop and think about what this means. Your atoms were forged in ancient stars. Those stars exploded, scattering elements across space. That debris formed planets. Eventually, it formed you. If information is never lost, then the detailed quantum state of those ancient stars still echoes within the fabric of the cosmos, transformed, diffused, but present. Black holes do not violate this principle. They dramatize it. They force us to confront the union of gravity and quantum theory. They reveal that space-time is not a passive stage. It is dynamic, thermodynamic, informational. Now things get strange. If space-time has entropy, if horizons have temperature, then geometry itself must arise from microscopic degrees of freedom. Just as temperature emerges from molecular motion, curvature may emerge from quantum bits. Gravity, then, is not fundamental. It may be an emergent phenomenon, a large-scale consequence of deeper informational rules. Same pattern, same physics. In this view, the universe resembles a vast quantum computation. Boundaries encode data, interactions process it, radiation carries outputs. What we perceive as space and time could be collective behaviors of underlying informational building blocks. Black holes are where this structure becomes visible. Their song is a clue. A thermal spectrum with a precise temperature, a relationship between mass and radiation, a shrinking horizon that reveals deeper laws as it fades. And at the end of evaporation, in that final burst, the accumulated story of everything that crossed the horizon must be returned to the universe in some encoded form, not destroyed, transformed. That transformation is the essence of physics. We seek laws that preserve consistency, symmetry, coherence. Black holes once threatened those principles. Now they illuminate them. Think about the journey, from the simple idea that nothing escapes to the realization that quantum fluctuations whisper at the boundary, from perfect silence to a faint cosmic hum, from apparent destruction to subtle preservation. That arc mirrors our broader quest. We confront darkness, we assume emptiness, then we discover structure, law, hidden order. Here's the thing. The universe is not silent. Even its most extreme objects participate in a grand conversation between gravity and quantum mechanics. Their song is quiet, almost imperceptible, but it carries profound meaning. It tells us that reality is deeper than surfaces suggest, that boundaries encode truths, that information is the currency of existence. And perhaps most importantly, it tells us that our theories are not yet complete. The black hole sings because space-time itself is alive with quantum possibility, because emptiness is restless, because the cosmos guards its information with unwavering fidelity. Listen closely. In the faint radiation of a dying black hole, you hear not merely decay, but continuity. Not silence, but structure. Not an ending, but transformation. And that is a song worth hearing.